equations of constant acceleration. So we are on page 11 in the textbook. Right, so if you only use these two formula, right, if you have a look at the two formula that we've got in the boxes over here, one very important thing about this is these formula are only going to work when we talk about constant acceleration. Okay? What can you tell me about constant acceleration, Dominic?
Constant acceleration is constant.
It doesn't change. Yeah?
Doesn't change.
What would it look like graphically?
A straight line.
More importantly, it will look like a
linear graph.
I want you to think about the actual acceleration graph. It will look like this. Oopsie. Right. If I picked an acceleration of, let's call it 1, my acceleration would look like that. Okay. In other words, it's the gradient of the velocity function.
Yeah, the big five, let's do that equation.
And it doesn't change. So if I asked you to graph the gradient of a straight line, well, that's what you'd get. It might not be 1, it will be whatever the value is of the gradient. Okay? Because the gradient doesn't change at all. It stays the same for any value. Okay? And that's what it visually looks like. That is constant acceleration. Okay? So what we're going to learn today is you would have realized from some of the homework questions that a lot of the times you had to use two equations to try and solve the same problem. Okay? And obviously this is error prone and it's time consuming. And so what we can do is we can manipulate the equations that we have, right? And we can come up with a set of formula that we can have at our disposal. They're like, you know, having weapons in your toolbox, right? The more tools you have, the better. Okay? So we're going to learn different types of equations. Very importantly, these only apply to constant acceleration. Okay? Right. Before we get to constant acceleration, if I didn't have any acceleration, if I only had constant velocity, what would my formula look like, Keanu?
Can we have constant velocity?
If I only had constant velocity, there's only one formula that I can use.
Yeah, I should open up. I have a picture with all of them on. I still have to memorize them all.
The most basic of basics. You learned it back in IGCSE, except you didn't call it velocity and displacement. You called it distance and speed. And what did it look like?
Oh, V equals D over T. Or V equals S over T. Sorry.
V equals? That was it. That's constant velocity. The velocity doesn't change. Okay? Except we know that velocity does change, right? Now we're saying, well, the velocity is changing, except the acceleration is going to be constant. Okay, and so we have a whole new set of formula for this now, because our velocity can't just be calculated by distance over time. Because it's changing, we need some new equations to work with. Okay, so the very first thing we're going to do is I want you to have a look at all the variables in the equation. And we're going to obviously spot there are some ones that pop up all the time, right? There's this A, V pops up quite a bit, U pops up quite a bit, T pops up quite a bit, and we have that S there. So before we even go forward, we're going to define, obviously, what all of these mean, and obviously it is vital that you remember what these are. Okay, so if we are talking about constant acceleration with velocity, does that S stand for speed, Zara, or what does it stand for?
Displacement.
It stands for displacement. Okay, very important. Oops, sorry. Right, what does the U stand for, Toya?
Initial velocity.
Very good. Initial velocity. Right, what does the V stand for, Dominic?
Final velocity.
Final velocity. So the moment you see a V and a U, you immediately know to yourself, this is not constant velocity. This is a change in velocity, and hopefully it's a constant acceleration. Because obviously if it's not constant acceleration, we can use none of these formulas. Okay, all of these formula rely on the principle that this is constant acceleration. Right, the A, right, will stand for the acceleration. And the T is just the time. Simple as that. And they will normally in textbooks and online and anywhere else you look, they will call these the SUVAT equations, right? And that's the way that I've written it over there. SUVAT. So displacement, initial velocity, final velocity, acceleration, and time. Okay. So the first equation, right? I don't like to just give you equations. I like to show you where they come from. And the very first equation, right, actually comes from one that we've already used, right, which has actually been manipulated, right, to look different already. And that's this guy over here. So this equation's actually already been manipulated. You actually don't get given this equation like this. It's given to you in a different format, right? So Toya actually changed the subject of this formula when he was answering question 10, and he turned it into something different. Okay, so if we multiply both sides by t, right, we will get a t equal to v minus u. And if I move the u to the other side, right, I will get v equal to u plus a t. Now, I wonder if any of you, have you seen something like this or something similar to this before? What about you, Kiana? Have you seen something similar to this before?
Yes.
What would you normally, what did you learn about this before when you were a young lad? Okay, I want you to not think about velocity and initial velocity. I want you to look at the way this is written, and I want you to think about an equation that you learned.
Oh, okay, yeah, this is acceleration equals velocity minus initial velocity over time.
No, right? Right, I want you to think very carefully, all right? If I have constant acceleration, right? If you go back and look at my little mini graph here for constant acceleration, this guy here, right? That acceleration is the gradient of the velocity curve, right? But actually it's not a velocity curve, it's a velocity line. That tells me if I have constant acceleration, that means I have linear velocity, right? Don't you guys know the linear equation? What does it look like?
Y equals mx plus c.
So all that's happened is we've just changed y has just become the velocity, u is just the starting velocity, a, the acceleration, is quite literally the gradient, and that is the definition of the gradient. It's the rate of change, right? And the rate of change of velocity is, by definition, acceleration, okay? And x being my variable. So as the time changes, the x velocity would be greater, right? So let's think about a very simple example, right? If you had an initial velocity and constant acceleration, and we set the constant acceleration at a certain value, right, a constant rate, the longer we hold that acceleration for, the faster our final velocity is going to be. Okay, so if you put your foot on the pedal for 1 second, you will accelerate the car a certain amount. If you hold your foot on the pedal for 5 seconds, well, you can think the car is going to go a lot faster, right? And the longer you hold your foot on the accelerator, the faster the car is going to go, right? So in other words, time being our variable tells us that the longer the time is, the greater or the less the acceleration will be. So there we have our very first equation. Okay? Only 4 to go. Right? And I'd like you to obviously think about this velocity equal to initial velocity plus at exactly as it is, right? It is just a linear function for velocity, right? With the gradient being your acceleration. Right, let's have a look at the next one. Okay. We're going to keep this guy over here. We like him. We like this guy here. He's equation number 2. Right? We can combine both of these functions, all right, to create another equation, right? So if I substitute the velocity from my one equation into my other equation, I'm going to get a new equation. So if I substituted, for instance, velocity into my displacement one, so I have displacement equal to a half initial plus final times t. What would happen if I substituted in my second equation? Dominic, what would I get? So I'd like you guys to quickly do that. I want you to take this equation here, and I want you to substitute it into this equation here. And I want you to see what you get quickly. I'll give you a minute to quickly do that. So you should have got something that looks very much like this.
This equals u plus half at squared.
Oops, sorry. ut plus 1/2 at squared. So there we have our next one. Okay, in exactly the same way, if I had changed this equation here, if I just made u the subject of the formula, right? If I moved the at to the other side and made u equal to v minus at squared, all right? I would have just ended up with this. Right, one more to go, all right? So we have now made a velocity the subject of the formula, and we made final velocity the subject of the formula, and we made initial velocity subject of the formula. Right, if we made time the subject of the formula, all right? Let's take the velocity equal to, or the linear velocity function, and let's change it quickly into a time equal to function, okay? So we would get, we can do this all at once, v equal to u plus at, right? We're going to move the u to the other side. We're going to get v minus u equal to acceleration times time. Therefore, time is equal to v minus u all over a. I'm going to substitute that into my displacement function and see what I get. So I'll write the displacement function over here. S is equal to 1/2 u plus v times t, all right? Except we don't want t anymore. We want to substitute t for what we've just created. So we will get displacement equal to 1/2 u plus v, right? And we're going to substitute in u minus v, v minus u, all over a. Right, I have 1/2 and I have this a on the denominator and I don't like it. So I'm going to multiply both sides of this equation by 2a. That will get rid of the 1/2 and it will also get rid of that a on the denominator. Okay, so I'm going to get 2as on this side, right? That 1/2 is gone because I multiplied by 2. I'm just going to switch this v and this u around in the bracket. I'm going to get v plus u. And I multiplied the a away as well, so it's also gone. So I have v minus u. And there we just have a difference of squares, right, which is very nice. So this is going to simplify into 2as equal to v squared minus u squared. I'm going to make v the subject of the formula. And so I'm going to get v squared equal to u squared plus 2as. Right, and that is our fifth and final equation for constant velocity. Okay. So Zara, why do we have all these equations? Do we like to punish you? Is there any particular reason you could think of why we have so many of these equations?
So we can use them so we can get the answer more quickly
Yes.
and
All
more
right.
accurately.
So it cuts down on the workload, all right, because sometimes we don't have all the variables, and you'll notice in certain of the formula, right, we tried to cut one of the variables out, okay? So in the very first formula, there's no acceleration. So if you aren't given acceleration, well, then you don't use the, you know you can use this formula over here, all right? The second one doesn't have displacement, right? These two which are similar, right? The one doesn't have final velocity and this one doesn't have initial velocity. So if those are things that you are not given, then you can use either one of these formula, right? And finally, the last one, we don't have time, right? So there's no time in this formula. It doesn't rely on us knowing the time. So that is why we learn all these equations, because sometimes we are not given enough information, right? And we could do multiple equations, right? And get simultaneous equations, or we could use the appropriate formula and get the answer straight away. So I would like to just compare this quickly for you guys with the formula that you are given in your exam, right? These are the formula that I've just copied from the formula sheet, right? You'll notice you're not given one of the formula. Who can tell me very quickly which one it is?
dt minus half at squared.
There we go. All right, so you're not given this one here, displacement equal to vt minus a half at squared. But hopefully, because we've seen how to derive these formula, you can derive it very quickly for yourself if needed. Or just remember it. They're very similar, the two. Right, let's grab our worked example quickly. And we'll quickly run through one of these before I let you go. So we have a go-kart. And this go-kart is traveling down a slope with a length of 70 meters. It's given a push and starts moving at an initial velocity of 3 meters per second and accelerates at a constant rate. Very important when we read that constant rate, right? We know we can use our constant acceleration formulas. Find its velocity at the bottom of the slope. So Dominic, what's the first thing I'm going to do before I even start trying to solve the problem?
Write down all the information that you were given.
Okay, so what information was I given?
You are given the distance or the displacement.
Displacement, yeah.
You're given its initial velocity. And you're given constant acceleration. Acceleration, oh my goodness, acceleration.
Oopsie, I've forgotten yes there. All right. Right, so the two bits of information that we are not given are time and final velocity. Okay, so we don't know time. And final velocity is the thing that we want to work out. Okay, so we could go about this and use multiple equations, or we could go and look at the equation that doesn't require us to know the time, right? And the equation that doesn't require us to know the time is the one that we worked out last. V squared equal to u squared plus 2as. It doesn't rely on us needing to know the time. And so that's the formula that we're going to use. We're going to say that v squared is equal to u squared plus 2as. And now we're just going to solve for v. We're going to put in the information we know and solve for v. Okay? So we know the initial velocity is 3 meters per second. We know the acceleration is 2 meters per second, and the displacement is 70 meters. Okay. That's going to give me my velocity squared of 9 plus, what's it going to be? 2 times 2 times 70. That is 142.80, so 289. And that means that my velocity is equal to the square root of 289, which is plus or minus 17. Right. Which of these is correct? Tway, I'll pick on you. Is it going to be minus 17 or is it going to be plus 17?
Plus.
Okay, and what would the reason be for your answer? You are correct. Don't backpedal, you're right. But why must it be plus 17?
Because I don't think it can be minus. Acceleration can't be minus, right?
Well, it could be, but it wouldn't be acceleration. It would have been deceleration. So if they said to you it decelerates, then you would have chose minus, right? Remember, for acceleration, your final velocity must be greater than your initial velocity. For deceleration, your final velocity will be less than your initial velocity. That's kind of the whole principle of acceleration and deceleration, okay? So our initial velocity was 3 meters per second. And so if we want acceleration, our final velocity must be 17, right? And very important, meters per second. Right, let's quickly do part B before the time runs out. Find the time taken for the go-kart to reach the bottom of the slope. So we have 2 ways we can try to solve this. One, we can use the information we got from the previous answer, all right? Alternatively, because we sometimes wonder, maybe I mucked things up and didn't get the first part of the question right, let me quickly restate the information that I have. And I want to look at a formula that helps me find time, but that doesn't rely on me knowing my final velocity. So if I look at the equations that I know, the only equation that does not rely on final velocity is this one over here, right? It doesn't rely on us knowing the final velocity. And so that's what we will use. We will rather use displacement equal to ut plus a half at squared. And we will just plug in the information that we are given. That's going to give me 70 equal to 3t. This half and 2 are going to cancel out, plus t squared. We have a quadratic that we have to quickly solve. T squared plus 3t, sorry, minus 70 must be equal to 0. Okay, I think that's going to be 10 and plus 10 minus 3 equal to 0. That's going to give me time equal to minus 10 or time equal to 3. So Zara, which one is it going to be? Sorry, that's not. Oopsie, sorry, 7. I'm thinking 30, not 70. Which one will it be?
7.
Right, why must it be 7?
Because t has to be greater than 0.
Correct, right? We cannot have minus time. There's no. We wish we could have minus time, but there's no such thing.